actually something that's covered in statics. It's not really covered in this book explicitly, but it's something that supposed to forget about this. Just struggle with it here. So when we're talking about distributed loads, the big issue here is we're usually talking about trying to find equivalent point forces to that distributed load. So let's have a coordinate system. Let's have some distributed load on edge. Let's try relatively arbitrary. We'll use up as a positive sense, change, and the load as a value described by the function x. So the actual load changes A to B units. This should be force per length. So pounds per inch or foot, or if it's force per area, then you need to know dimension out of the point, so to speak. Right? This edge, right? Distributed load sits out here. You need to know this dimension, and then you multiply that value by that dimension. That's as force per length squared. Multiply it by that thickness b, which is length. Appropriate force. So, all right. Now, what we want to try to do here is find an equivalent force, its value, and its position. Right? That's equivalent to that distributed load in the sense of maintaining static. So, obviously the magnitude is important, but also the location is important because it affects some components, right? Okay. So, this magnitude F, you get by simply integrating over the entire distributed load. So look at a little region here. Delta X. There is some differential force there, dF. Total force is integral times that differential force. Now that differential force, right, is equal to W of X times, so this now is just the integral A W X. Right? So it's the area under here. Just integrate it, that's the total force. Alright. Now where does that stand? Right? Where should you locate that force to make it equivalent to the distributed load? Let's see. Alright. You can do that by doing some moments around. So let's do some moments around this point A. So basically, what we're trying to say is, well, let's put this combined actually. This position. Most often, relative systems. Right? That's typically the situation. Once you do it for a triangle or prime, so let's do it with respect to one image. Right? So what we want is if we have this equivalent force, its moment is equal to F times its moment. Right? That would be the moment around point F. Right? x bar, such that that is actually equal to the integral differential moment. Okay? So this is the actual moment of distributed moment. So we want to keep this. Now this distributed moment, if you look at it, this is df, right? This little differential force from this little differential element produces a moment around A of x minus A. I'm sorry, df. So here's the differential force. It's moment arm. Already know that df is equal to right? So now f bar integral A x minus A w x. Okay? Now, if you want to divide by f, x bar is equal to 1 f x minus A x. Know that f here is just w, so this is x minus A w of x dx over integral x. So that's the location. If you look at this, this is central of this area. Okay, that is by definition the central of that area. You can see it a little more easily if we imagine that x goes, that A goes to 0. In other words, at this point, the load starts at x equals 0. You shift the coordinate or something like that. That's the situation. You can see that this just gives us x bar equal x. Okay? See that that is the central. That's the definition of the central. Right? If you're not used to seeing these, you should go back and review it. We will use this thing later on when we talk about geometric quantities like J, I, Q. But if you look at this, sometimes this is called the first moment. It's called the first moment because it's the function W weighted by x to the first power. This is also called the zero moment because it's 2x to the 0 power of 1. And we'll also later on deal with second moments where we have an x squared in. That sort of stuff. Okay? That's how you find it. So practically what you do with this, we've seen this sort of stuff. So this. So what you want to take away from this is total force is area under the curve, and the location of that force, effective force, is at the center of that area. I mean the curve, that's the low now. So the obvious case is the uniformly distributed. uniformly distributed load as distribution of, let's say, 10 pounds per inch. Now, very often they'll call it W in the text. They won't really give X because it's constant. It's not a function of distribution. It's a traction of distribution. Let's say this goes from this location, 5 inches. Now, okay, so what's the effective force of this? I think should be able to do this even. Remember the centroid part. Area under this curve, total force is 10 pounds per inch times this length and this length here. 7 inches. 7 is 5 is 12. And so this one's 70 pounds, right? This comes from 7 inches times 10 pounds per inch. Let's cancel out. That's the effective force. Now its location is at the centroid. Before the integral, you know the centroid of the rectangle, right? So effective force here is 70-pound force acting. So that's 3.5 inches on this edge. 3.5 plus 5, so it's 5 inches. Okay. Do other ones. The next most common one you see is a linear distribution. Well, actually, let's do a triangular distribution first. Triangular distributions. So let's imagine distributed load goes as follows. A lot of times, that's where it says this peak load here is 20 pounds per inch. Let's say this line here is 10 inches. All right. So the area under the curve in this situation is the 1/2 base times the height. So the area here is 1/2 base, which is 10 inches, times the height, which is 20. Again, you can see this is pounds, this is 100 pounds. So that is effective force. Okay? That's equivalent to that distributed load. Now, where is it located? All right. Well, this one's one that's probably worth memorizing. For a triangle, that's a third, right? By thirds. And obviously, it's going to be closer to the higher end. So, it's 1/3, and then this is here. It's 2/3. Times the length, so it's 2/3 of 10 inches. 1/3 of 10 inches. So that's the location, right? So that would be this edge. 2/3, that's 6. 7 inches. Probably usually, we don't really talk strictly about significant digits, but in this class, it's not a bad idea to keep things at 3 significant digits. Less than 3 significant digits, you start to see some error, subtraction, and more than that, this one makes sense. So that's where that would go. You could also get that location from the integral. So in this case, you wanted to actually perform the integral, you have to know the distribution. So the distribution in this case is going to be 20, 10 times x. So that's a function, right? That's WX. Okay. You can go from 0 to 10 WX. Get that. And you can see that's just 100 pounds. 0 to 10, 2x, x, so we get x squared, x squared from 0 to 10, and then, right? And you also get a location, that's going to be 1 half 0 to 10 of x times x, which is 100 pounds. Once you go from 0 to 10, and x is 2x squared x, and thirds is 100 pounds. And then 2/3 x cubed greater than 0, which is, and then it's 2. Okay. Now what's useful is also looking at composite areas. We get this a lot. So, for example, so let's say you have a distributor that looks as follows. Y, X. Okay. It's trapezoid. Now, you can look at this and you can think of this as a triangle superimposed on top of a rectangle. So this is equivalent to X, Y, uniform distributor load, and triangular distributor load. So we can make this actually effectively two forces. You can use just the point force of the rectangular portion at the centroid, and then also put a point force at the centroid of triangle on its back. So this can be replaced with two forces. And actually that's fine. You know what I mean? You can then go combine them if you so choose. Right? But you use the force from the rectangle. And also the force from the triangle. You can settle up into one effective force. It's usually not that. So, I mean, number calculation wise, it doesn't become much confusion. Okay? So, example of that. So let's say it starts over here. Let's go from the top. This length here, let's make this 4 inches. Let's do meters. 2 meters. It's 2 meters. Let's say this starts off at 10 kilonewtons per meter. Goes up to 20 kilonewtons per meter. Okay. It's a trapezoid. If we break it up into the two sections. All right, the rectangle, it's going to act right through the center, which is 1 meter in. Dash this magnitude is going to be 1/2 base times height. This area, so it's 2 meters times 10 kilometers per meter. So it's going to be 20 kilometers. Right? Now we're also going to have one that comes just from this triangle region here. Triangle here. Sitting on top of the rectangle. That's going to sit at 1/3 in this edge. So that's going to be 2 over 3 meters, right? And its value is going to be the 1/2 base times height. So in this case, height is another. I screwed this up. I'm sorry. The height here is 10. Yeah, that's right. That's right. So the height here is 10 kilonewtons per meter. That's the height. Base is 2. 1/2 of that stuff. 10 kilonewtons. Okay? So you would have both those forces acting. That would be equivalent to that one. Now just to do one last one. This will come up once in a blue moon, but actually it's not too much. And actually, I'm doing this for a reason. I wanted to show you Mathematica. Pause, because I need to restart Mathematica. Pause, 1 second. Pause, please stop.